Hello everyone, my name is Ying Li. The title of my paper is Influential Community Search over Large Heterogeneous Information Networks. Nowadays, heterogeneous information network, also called HN, is a representative type of graph in our life. The most important feature of HN is that HN contains multiple template entities and multiple template links, such as DBLP, which is a famous and popular HN that contains 4 unique vertex types, also paper, topic, and venue, and TMDB, IMDb, and DBPlin. An important research topic in the graph area is the community search, which has found many real applications, such as event organization and product recommendation. In this paper, we focus on the topic of community search over HN. First, let me introduce the definition of HN, which are networks with multiple template entities and multiple template links, where entities represent objects and links denote different semantic relations. For example, in DBLP network, the edge linking author and paper denotes that the author writes the paper. The edge linking paper and venue denotes that the paper is published in that venue. Generally, each HN follows a schema, which defines the allowable vertex and edge types. Besides, with an HN, each entity is typically associated with an importance value. These values are heterogeneous in nature, which means for vertex of different types, their importance semantic meanings are different, and their values are in different ranges. For instance, in the DBLP network, we typically use the H-index to represent an author's importance value, and the value of the H-index usually ranges from 0 to 300. On the other hand, the importance value of a paper is determined by its number of citations, commonly varying from 0 up to 100,000. There are some existing community search works on HN. Reference 2 introduce KP-Cal model as a community model on HN. First, to model the relationship between vertex of the same type, researchers introduce the concept of metapath. Metapath is a sequence of vertex types and edge types, which can be derived from the HN schema. For example, author paper author connect two authors through their co-author paper. KP-Cal is a maximal set of p-connected vertex, where each vertex has at least kp neighbors. For example, at kb3 and metapath pb author paper author, we can find that A1, A2 until A7 forms a 3p-Cal from figure A, since each author can be connected at least 3 other authors via metapath. Now, let's talk about the motivation behind of the influential community search over HN, also called ICSH. Like we said before, entities in HN usually have some kind of importance value, but all the existing community search ignore the importance value of objects in the HN. This makes us wonder, how can we find the influential community in HN? In this work, a community is a set of vertex with the target type. The influence of a community can be modeled by considering not only the target vertex, but also the vertex connecting them. Since the importance values are of heterogeneity, so to consider the importance values of different types of vertex, we introduce the concept of an influence vector. Given an HNH, a metapath P, and a P-induced sub-HN G, we use the smallest value of each type of vertex in G to represent the importance value of this type. Therefore, for an HN G with H different types of vertex, its influence vector has H dimensions, and is represented as Fg. To compare the influence vector of two HNs, G and G', we introduce the idea of dominate. Particularly, if you have two different influence vectors, Fg and Fg', both with H dimensions, we say Fg' dominates Fg. If for every I from 1 to H, Fig is less than or equal to Fig', and for some I, Fig is strictly less than Fig'. For example, the influence vector 21,600 is not dominated by the influence vector 50,400. Based on the influence vector, we formally introduce the heterogeneous influence community, also called HIC, given h and h, a positive integer k, and a metapath P. An HIC is a set S of vertex with a target type. If there exists a set phi of passiness of P between them satisfying the following properties. The first is link cohesiveness. It means that each vertex in S has at least kp neighbors in S. Second is scalar importance. It means that the influence vector of H phi cannot be dominated by any other p-induced subgraph of phi prime. Third is maximality. It means that on the premise that property 1 and 2 are satisfied, the size of S is maximized. Here, the SIH problem is that, given h and h, a positive integer k, and a symmetric metapath P, return all the HSAs from H. For example, let KB3 and PB also paper also. We can find two HSAs S1 and S2 from figure A. SSH can be used in various real-world applications, such as organizing events, supporting recommendation tasks, network analysis, and so on. Now, let me show you a case study. We run an SSH query on a small DBLP network. For organizing an academic workshop, we request that each author has at least 5 co-authors, which are described by the metapath, author, paper, author. The figure shows the two communities we find. From this figure, we can see that the authors of the first community have high H-index values. These authors are from MMLab and CHK, which is a really well-known computer vision library. They have written some good papers. About the second community, even though some authors don't have high index value, when we look closer, we found out they published a big table, which is a big deal in the systems field. That's why these papers are cited a lot. Also, something interesting is that 2 of the authors from this community aren't really active in research anymore. That's probably why the H-index isn't high. Now, let me introduce our algorithms to solve the SSH problem. Let's first dive into the basic algorithm for HB2, which we call basic 2D. The main idea of basic 2D is follow the algorithm of traditional scalar query. Here's how it works. First, we fix a value f1 of one dimension and maximize the value f2 of the other dimension. Secondly, we increase f1 to the minimal value that is larger than the previous value and then repeat step 1. For example, let KB3, PB also paper also. We first fix f1 be 21 and maximize the value of f2 by deleting p2 and p1. Particularly, we first remove p2 since p2 has the smallest importance value among all papers. After p2 is deleted, we can still find a 3p call in the chain, so we move on and remove p1. After that, we can't find a 3p call anymore, so we move to the next step. Secondly, we fix f2 be 100 and try to maximize f1. When we remove a4, we see that in figure A, we can't form a 3p call anymore, so we end up with an influence vector 21 and 100. Even though basic 2D is straightforward, but it will remove vertex multiple times, leading to much redundant computation. To overcome the drawbacks of basic 2D and improve the whole efficiency, we design an advanced algorithm faster 2D. We propose the concept of target key node. A vertex U with target type in H is a target key node. If there exists a KP call such that the minimal importance value of its vertex WU, a key feature of the target key node is its bijective relationship with communities. By calculating all target key nodes, we can subsequently compute all HSAs based on this relationship. To find these target key nodes, we keep removing vertex with the smallest importance value in the KP call. For example, at KB3 and PB also paper also, we first remove A file since A file has the smallest importance value among all authors. Then we remove A file. After deleting A file, we find that a 3p call can't be formed in the HN, so A3, A2, and A1 are all removed. Here we identify two target keynodes, A5 and A4. Hence, the important steps of FAST2D is that we first compute all the target keynodes. And secondly, for each target keynote U, we first fix F1 BW, and then compute the upper bound of F2, denoted by the F2 hat U, and finally shrink F2 hat U to its actual value. For the case HB3, we first give a basic algorithm basic 3D. This algorithm is straightforward. We first fix the second or third vertex type, and then invoke FAST2D to enumerate all the possible importance values of vertex to obtain the HSA. The disadvantages of basic 3D is that generate many influence vectors that are dominated by others. To improve the efficiency, we propose an advanced algorithm, FAST3D. We first identify all the target keynodes, and secondly, we prove the search space by the upper bound of the influence vector corresponding to each target keynode. Finally, we enumerate all the possible F2, F3 on the bounded search space. For example, we can say the bounded search space is tighter than the initial search space. Here I will present the experimental results. First, I introduce 4 datasets used in our experiment. We use 4 real HS, TMDB, DBLP, IMDB, and DBPLin. Where for TMDB and DBLP, the nodes have the real importance values, while nodes of IMDB and DBPLin, the nodes importance values are synthetically generated. Figures below shows their numbers of vertex, edges, vertex types, and edge types. Then I want to introduce our experimental setup. By default, we set the value of k to 5. For the first 3 datasets, we collect all the map paths with length at most 4. For the last one, we collect 15 map paths of the highest frequency. We also compare our ICH query with CH query, and we first use ICH query to identify communities, and then use the vertex with the highest importance value as a query to execute the CH query. To evaluate the influence of the community, we first compare the average vertex importance values on communities. It is clear that ICH can obtain the more influential community. Besides, we use several metrics to evaluate the quality of communities. We use diameter and density to evaluate community compactness, and use PathSim to evaluate similarity of community members. It is clear that our ICH has the smallest diameter and has the largest value of PathSim and density. In summary, our ICH query has 2 advantages over CH query. First, it can obtain the more influential community. Secondly, the communities it finds are more compact and cohesive than that of the CH queries. Now, I will show you efficiency evaluation of our query algorithms. Here, basic half-2D is the basic 2D plus binary search. The figures shows the efficiency results of query algorithms by varying k. Clearly, FAST2D is up to 2 orders of magnitude faster than basic 2D and basic half-2D, since for each vertex can only be deleted once in FAST2D. In addition, FAST3D is at least 2 orders of magnitude faster than basic 3D, indicating that our search space pruning strategy is effective for facilitating the queries. Now, let's talk about the related work. There are numerous studies focusing on non-influential community search and influential community search within homogeneous graph. Additionally, some research focuses on non-influential community search in heterogeneous graph. Below are some important works. For homogeneous graph, non-influential community search primarily invoke k-core community and k-trust community. As for influential community search, mainly centered on influential community and scanline influential community. For heterogeneous graph, the primary focus for non-influential community search is on KP-core and K-phi AMC. There are some reference papers. Hence, in this work, we study the influential community search over heterogeneous graph. Thank you for your listening.